The next phenomena we're going to have a look at now is the photoelectric effect. Now this was discovered by Hertz in the late 1800s when he was conducting another experiment, without going into too much detail, part of the experiment there was a spark that was being produced, and in order to see the spark he placed his apparatus into a darkened box, and he found that the spark was actually smaller when it was in the darkened box. When it was outside in the light, the spark was bigger. He started to sort of make some observations and basically developed into the photoelectric effect. So basically this phenomena was sort of discovered by accident somewhat, and there are a few things that are particularly important about it, and I'll just summarize it really quickly. For the photoelectric effect, we're basically looking at the fact that light can immediately displace electrons from the surface of a metal. So the reason why Hertz was noticing the difference in his observations, in the absence of light, there were none of these electrons being emitted, and so the spark was smaller. When light was present, then there were more electrons, and so the spark was bigger because of the extra charges there as a result of the photoelectric effect. So light can immediately displace electrons from a metal surface, but only when the light had a high enough frequency. So there was the first important thing to identify about the photoelectric effect. The second important thing to note is that increasing the intensity had an effect on the outcome, and it would seem that if you increase the intensity, you've got more energy there, so the electrons should come out with more energy. But what was actually observed, increasing the intensity of the light displaced more electrons, but they didn't have more energy. So it didn't increase the kinetic energy of the electrons. So that is sort of the photoelectric effect in a nutshell. But we need to look at exactly how how this phenomena occurs and what it is that's actually going on. And the person that's largely responsible for that is Albert Einstein. And he did that by going back to Planck's theory that we mentioned in the last video about energy occurring in quantized amounts. And so by applying Planck's theory, what he saw, or what he was able to propose, were a couple of key aspects about the photoelectric effect. So the first was that energy occurs in packets, and this is basically sort of what Planck discovered himself. So energy occurs in packets, and the equation that we use for that relationship is E is equal to HF. Now that's an important equation to make sense of. It's one that's in the data booklet. So basically, if you want to know what the energy associated with a particular frequency of light is, you use the equation E equals HF, where the value H is known as Planck's constant, and it has a value of 6.63 by 10 to the negative 34 joule seconds. Now that's a quantity that is also in the data booklet, so it's a constant, so you don't need to memorize it. You can just look that one up. The second thing that he proposed then was that a minimum energy is needed to displace electrons from the metal surface. So that kind of makes sense when we think about our understanding of atoms now, given that the electron's going to be fairly tightly bound in the metal lattice, and so in order to pull it away from the metal lattice, you're going to need to do a certain amount of work on it, and so that means a minimum amount of energy is needed, and that minimum amount is known as the work function. And the work function has the symbol phi, and the equation there, it's not too dissimilar to the one above, would be hf naught. Here, f naught we're going to call the threshold frequency. So the work function is just an amount of energy that corresponds to the energy needed to remove the electron. Note that that's not an equation that's in the data booklet, but one that you'll need to be aware of, have in the back of your mind. The next point then, if a photon has an amount of energy that's less than the work function, so if E is less than the work function, or another way to put that, the frequency of light is less than the threshold frequency, then no electron is displaced. Doesn't matter how intense the light is, the electron's never going to be displaced from the metal. Conversely, if a photon has more energy than the work function, so if E is greater than the work function, or if we do that in terms of frequency, F being greater than the threshold frequency, electrons are displaced, or an electron I should say, and the electron will be immediately displaced. So it's not like it takes a while for the electron to sort of get up enough energy. The electron is immediately displaced. We'll come back to that idea a bit later. And the excess energy of the photon can be transferred to the kinetic energy of the electron. Sorry, can be transferred. Now, we are going to look at the sort of the extreme, I suppose, and deal with the maximum kinetic energy here. Given that, so if you think about an electron as it's being pulled away from the surface, there are going to be some electromagnetic forces of attraction between the charged particle and the nuclei that it's leaving behind. So it may lose some energy as it comes out, but the maximum kinetic energy will be given by the difference between the energy supplied by the photon and the work function. So E is equal to HF minus phi. So that's the maximum kinetic energy that's possible. We are going to see that there will be lower energies of the ejected electrons, but the maximum kinetic energy is just the difference between the energy of the incoming photon and the work function itself. Now, if we look at that in a graphical sense, so we'll deal with a graph where we have the frequency on the horizontal axis, and on the vertical axis we're going to have the maximum kinetic energy. So only dealing with the maximum, we don't really care about anything less than that, just the maximum. So we would have a threshold frequency F naught for a metal. Let me just change colour to make it a little bit more obvious. So for this metal, below that threshold frequency, the maximum kinetic energy is going to be 0 because there are no electrons that will be emitted. Above that, we're going to see that there is a linear relationship given by E equals HF minus phi. So the gradient there is going to be H, Planck's constant. If we were to project that line back through to the vertical axis, just extend that down a little, that value there would be that value of negative phi. So we can interpret the vertical intercept there as being the value for the work function. Now, if we're dealing with a different metal, that means it's going to have a different threshold frequency. So if we have using a different colour here, so let's find one that's nice and clear. So if we have a different metal, that means that it's going to have no kinetic energy up to a higher threshold frequency, or it could be lower depending on the metal, but we're still going to see that increase after that threshold frequency where the gradient will still be H. So this call this one metal 2, and the first one metal 1. And so we would then have all sorts of different metals, or all of the different metals would have different threshold frequencies, different work functions. And so we'd see a different line for each of those metals. And so we could use the threshold frequency then to determine what particular metal might be used in a given experiment. Now, one of the other critical things about this idea of the photoelectric effect is linking it back to the wave model. And there are a couple of key things that the wave model and the syllabus itself actually outlines that this is a key point to be able to identify. So the wave model could not account for two specific things. There are a couple of other sort of little bits and pieces along the way as well, but these two are the two that you should really be aware of. First thing is it couldn't account for the immediate release of electrons. And the reason for that is that if you go back and think about the wave model, if we think about energy being continuous rather than discrete or quantized as we are now dealing with, that would suggest that any wave or any frequency, we should be able to have electrons being ejected. And the reason for that is that if energy is continuous, then as a wave is, or as light is being shone onto a surface, it should mean that eventually there should be enough energy that an electron could be emitted even for low frequencies. So the energy would continue to build up, and eventually there'd be enough that the electron could gain that energy and be displaced from the surface. So that should cause electrons, or should eventually cause electrons to be emitted or displaced. So that particular aspect just sort of doesn't work. We don't see any electrons being emitted below the threshold frequency, but above we see that there are immediately electrons emitted even for just a single photon. So for a single photon with high frequency, an electron is immediately displaced. Not could, it would. So there's the first thing, that the wave model is where it's insufficient. The second ties back into the intensity that I mentioned earlier. So with intensity, so the effect of intensity can't be explained by the wave model. And the reason for that, if we go back and think back to, I think it's Unit 4, if we're dealing with a wave, for a wave, the intensity is proportional to the square of the amplitude. And amplitude basically relates to energy. So a greater intensity means that we should have more energy. So for a greater intensity means more energy, and so we would then expect electrons should be emitted with more energy. So the electrons should have more energy when they're displaced. Instead, what was observed is that the observation showed that the energy of the electrons was no greater, the maximum energy, I suppose we should really identify. So the maximum energy of the electrons was still the same for a greater intensity, but there were more of them. So we can I'd get back to that idea that in this particular scenario then, what it really means is that greater intensity means more photons, but not higher energy photons. So more photons, all with the same amount of energy. So another good example of where our understanding has been developed purely by observation and making sure that we adjust our understanding because the observations that we make don't match with the theory, so we need to adjust the theory in order to accommodate these new observations. We'll have a look at a few problems where we're dealing with the photoelectric effect, the equations in particular, and graphical interpretations in class.